Well, we're going to start chapter 8 today, and it has applications to the COVID-19 virus, interestingly enough. We'll say that a differential equation, that's the topic of the chapter, is an equation for some function y of t, dependent variable of an independent variable, involving one or more derivatives of y. Such as a function of t, y, y prime through y n minus 1 means n minus first derivative of y. We can't make n minus 1 hash marks there. Equals 0. This is an arbitrary equation involving t, y, and some of the derivatives. If it involves at least one derivative of y, then we call it a differential equation. We'll say it is nth order if n, let's say this goes up to nth derivative here, we'll say this is the nth derivative of y. If yn is the highest derivative that appears. Now, differential equations in general tend to have an infinite number of solutions in practice. For example, this one. Y double prime plus 4y equals 0. How can we test if something's a solution? A solution of a differential equation, I'll write DE for short, long pair of words, is a function y of t that satisfies the equation, that's all. For instance, suppose I consider y1 of t equals sine of 2t. Is that a solution to this differential equation? You can test it just by taking its derivatives and plug it in. This is a second order differential equation, because the highest derivative is the second derivative. Now, if you take this function, its first derivative is the cosine, twice the cosine, right? Derivative of sine kt is k cosine kt, you'll recall. Let me fix this. And then the second derivative is the derivative of 2 cosine 2t is minus 4 sine 2t. When you plug this in, for y double prime you have minus 4 sine 2t. When you plug in for y, you get sine 2t. And you plug in the function and its second derivative on the left, and what do you get? Minus 4 sine 2t plus 4 sine t equals 0. Sure enough, it satisfies the equation, so sine 2t is a solution. But it's not the only solution. So some of the problems just say, see if this is a solution, all you have to do is calculate its derivatives and plug in. Similarly, y2 of t equals cosine 2t has first derivative minus 2 sine 2t, second derivative minus 2 cosine 2t, and you plug in on the left y double prime, oops, this is minus 4, sorry. And you get minus 4 cosine 2t plus 4 times, plug in y cosine 2t. Well, minus 4 cosine t plus 4 cosine 2t is 0. Sure enough, cosine 2t is also a solution. And in fact, you can show in differential equations class that any function c1 cosine 2t plus c2 sine 2t is a solution. You can plug this in with arbitrary constants in it. So if you take c1 y1 plus c2 y2, this is a solution. So you take the derivative and you get minus 2 c1 sine 2t plus 2 c2 cosine 2t. If you take the second derivative, you got minus 4 cosine 2t minus 4 sine 2t, and you can plug this in for y double prime and get minus 4 cosine minus 4 sine, and then add 4 times y, which is cosine, I forgot my c1s here, c1 and c2, forgot my c1 and c2, plus 4 cosine, c1 cosine cosine 2t plus c2 sine 2t, and you see that these all cancel out. This one cancels this one cancels this one, and you get 0. Any function of this form is in fact a solution. These things tend to have an infinite number of solutions in general. Well, that's how you test to see something's a solution. Just plug it in and see. And it may have an arbitrary constant and still be a solution. Here's a very simple example. Suppose I had y prime equals 2.6y. You've heard that each person on the COVID virus infects about 2.6 others, right, in one time period. Maybe it's a few days, right? And so the unit of time is a few days or so. Y prime equals 2.6y. How can I solve this? Well, I will rewrite this actually as dy dt just for purposes of making this look a little easier. I can divide through by y and write this as 1 over y dy dt equals 2.6, and then I can integrate both sides with respect to t. And what I get on the left, well, by u substitution, if I let, or y substitution, I make this dy dt dt is equal to dy, and I can rewrite this as integral 1 over y dy equals integral of 2.6 dt is 2.6t, and then there's an integration constant. What I get on the left is ln absolute value of y equals 2.6t plus an arbitrary constant. There's the solution to the spread of COVID-19 problem. And if I take the exponential of both sides, now I've got absolute value of y equals e to the 2.6t plus a constant, or if you like, absolute value of y equals e to the c times e similar thing when I divided through by y, I assumed y equals 0 wasn't a solution. If you go back and check by plugging in, the derivative of 0 is 0, the right hand side is 0, 0 is a solution. So not only is e plus or minus any constant times e to the 2.6t a solution, the general solution, when you include the y equals 0 solution that we previously omitted, is y equals an arbitrary constant, we'll call it a, where a is plus or minus e to the arbitrary constant c, or 0, a e to the 2.6t. There's the general solution to this differential equation. It points out that we haven't got how many people get infected by the COVID virus. We've only got a general solution. What's missing here that we get the exact number of people that are infected, right? Well, in practice, what people like to do is give, instead of a differential equation by itself, a differential equation with values for y and its first n minus 1 derivatives for an nth order equation. So we'll say an nth order initial value problem to try and get a unique solution. And we'll abbreviate that IVD, is a differential equation dE of nth order. Means it has derivatives through n with n initial values. Usually given at t equals 0, but they could be at some other value. So we'll say y at t0 is equal to some number we'll call y0. At some time you have this many infected or something. Y prime of t0 is equal to y0 prime, and so on. We want the n minus first derivative at t0 equal to y0 n minus first derivative. So this is a number on the right. The n minus 1 doesn't indicate derivative here. It's just notation for the number that is the n minus first derivative at t0. So on the right are all numbers, and on the left are y and its derivatives evaluated at t0. So that's an initial value problem of nth order, is an nth order differential equation with initial values for y and its first n minus 1 derivatives. Let's go back to the problem we had. Now, consider the differential equation dy dt equals, equals 2.6y together with an initial value. Since it's a first order equation, I only need one initial value. Y at time 0, let's say, is 100 people. Initially you start with 100 people. And how many become infected if each person infects 2.6 others in some time period, and they infect 2.6 others and 2.6 others. You get this kind of a growth model that the rate of increase of the infected is proportional to the number of people currently infected times 2.6. So we already know that the general solution of the differential equation is y equals a e to the 2.6t. And now we apply the initial value that when t equals 0, y equals 100. That's what the initial value says. And we get 100 equals a e to the 2.6 times 0. Well, e to the 0 is equal to 1. So a equals 100. And we get a unique initial value problem solution. That's the purpose of the initial value. That y is equal to 100 e to the 2.6. That's 2.6. T. If you check this out, this is a pretty fast growing function, and that's why you get so many people getting sick so quickly. All right, so there's a solution to a very simplistic model. What happens in practice, actually, is that this doesn't keep growing forever. what we eventually get to is the point where you can't infect so many people because so many people are already immune, and then the equation ceases to increase exponentially like this, or the solution ceases to increase exponentially like this.